Alrighty, howdy folks. Let's look at Chapter 4, Section 4. This is about non-homogeneous linear equations with constant coefficients. If you recall, up until 4.3 or in 4.3 rather, we looked at homogeneous linear equations with constant coefficients. But now let's learn about non-homogeneous linear equations with constant coefficients. Okay, what would be the form of an nth order linear non-homogeneous ODE with constant coefficients? It would look like this: a sub n d to the ny dx to the n. Here, a sub n is not any generic function of x, but it's just a constant. Similarly, a sub n minus 1 is a constant, and so on. So all these a sub 0, a sub 1, so on are all constants. Okay? Excuse me. And more importantly, the g of x on the right-hand side is not equal to 0. If you recall, for a homogeneous equation, the g of x must be 0, right? Cool. Now we want to figure out how to solve these kinds of equations. So as a motivation, let me ask you this. Would you say is y equal to 2 a solution of, if I asked you this, is that as y equals to a solution of the differential equation? How would you proceed even? Well, you just plug in y equals 2 into the differential equation and see whether or not you get the left-hand side equal the right-hand side, right? If y equals 2, dy dx is 0, plus 3 times y is 3 times 2 is 6. Hey, that's exactly what the right-hand side is. So then, now I ask, is y equal to e to the negative 3x plus 2 a solution of this? What? I thought we already said y equals 2 was the solution. What's up with my question here? Yeah, that's the whole idea. So, is this a solution also? And turns out, I don't know if I showed it here. Yep, it is also a solution. Trust me, if you differentiate and plug and all that, you get left-hand side equal right-hand side. So, the question is, where did that e to the negative 3x come from? I thought shouldn't we be satisfied that we showed that y equals 2 is a solution, and so that's it? No. The truth is, even if we were to add e to the negative 3x to this existing 2 as a solution, that turned out to be a solution. And the thing is, where did it come from, right? From solving dy dx plus 3y equals 0. But I thought the original equation was dy dx plus 3y equals 6. Yep, that's the idea. If you were to solve what is called a corresponding homogeneous equation, you will get a certain solution. Right? Let me repeat that. If you, given a non-homogeneous equation, if you were to solve the corresponding homogeneous equation, what do I mean by that? Set the right-hand side equal to 0 and solve that equation. We know exactly how to solve equations of this kind, right? Constant coefficients, homogeneous, 4.3 stuff. So that's where it came from. Now, why should it make sense that by adding the solution of the homogeneous equation is how we get a more generalized solution to this? It makes sense because if we plug y equals e to the negative 3x into the left-hand side of the differential equation, what do we get? Any ideas? Has to be 0 because that is the solution of the corresponding homogeneous equation. So if I'm claiming that e to the negative 3x is a solution of this homogeneous equation, that means if I plug e to the negative 3x for y, I must get 0. Okay, so if you plug 2, you get 6. Right? We already showed that. So if we add e to the negative 3x and plus 2 and try to plug that in, we get 0 due to e to the negative 3x and 6 due to the 2. So 0 plus 6. So that is in fact a more generalized solution than just 2 alone. So this illustrates a general principle of linear homogeneous equations. Okay. So let me give a more formal definition of all of this stuff. Suppose you were to have a non-homogeneous differential equation with constant coefficients. In fact, the coefficients need not be constant. This concept applies even if you just have a linear equation, meaning a sub n minus 1, they could be any functions of x, need not be just constant functions. What happens is the general solution y is actually made up of what is called y sub c, which is the complementary solution, and y sub p, the particular solution. How do you get the complementary solution? By solving the associated homogeneous equation. Okay. But how do you get the y sub p? That's a different story. Okay, how to find y sub p is the only thing that we need to really learn, because we know how to get the complementary solution, and in this section we will find how to do that. Okay, in the previous example, we got dy dx plus 3y equals 6. For that differential equation, we got the general solution to be y equals e to the negative 3x plus 2. Can you figure out which one constituted y sub c and which one constituted y sub p? Right? What is y sub c? It's the complementary solution, which is the solution of the associated homogeneous equation. Didn't we find that the associated homogeneous equation had e to the negative 3x as its solution? So that's the y sub c. And the other one, plus 2, the 2 is the y sub p. As simple as that. Okay. Next, here is the idea. To find y sub p, we must assume a suitable y sub p based on g of x. Okay, again we go with this assume, right? But it's not just a stupid assumption, just randomly pick whatever we want. There is some sensible way of picking the y sub p's, and all that is based on the g of x that we have. So first, suppose we were to have the g of x to be an nth degree polynomial. Okay, what should we assume for y sub p? An nth degree polynomial. As simple as that. Is it easy to remember? Let me illustrate with an example. Is this g of x a polynomial now? What degree polynomial is it? Exactly, third degree polynomial. So what should we assume? A third degree polynomial. The only thing is, you must assume a general third degree polynomial. What do I mean by general or generic third degree polynomial? What I mean is the coefficients of x cubed, x squared, and all of that are unknown quantities. Some constants a, b, c, and d. Cool? And the whole idea is, once you assume like this, we should have some way of figuring out the constants a, b, c, d. And depending on the specific g of x, we can actually find, and the differential equation, we can actually find the values of a, b, c, d. Okay. Right now, I'm not focusing on how to find the constants a, b, c, d. I'm merely going to focus on, in this whole table, by the time I get done, we will fill up this whole table. Okay. We are focusing on, given a g of x, what we should assume for y sub p. Cool. Second, what if we were to have an nth degree polynomial times some e to the ax? Okay. Guess what? We must assume, maybe I'll let you take a guess. What do you think we should assume for y sub p? You guessed it, nth degree polynomial times e to the ax. Let me give an example or two for that one. Do we have an nth degree polynomial times e to the ax kind of a thing? What degree polynomial do we have as a coefficient of e to the 3x? A second degree polynomial. So here y sub p should be a second degree polynomial, a generic second degree polynomial, times e to the 3x. That is ax squared plus bx plus c times e to the 3x. Simple enough? Cool. I have another example. Wait a minute. Do we have an nth degree polynomial times e to the ax? No, we just have a constant. Is a constant a polynomial? Yeah, it is. It is 0th degree polynomial. So there's nothing wrong with a constant being the coefficient of e to the ax, okay? Well, if that is the case, in our case, in the y sub p, we will assume a generic 0th degree polynomial. That means a generic constant a. Okay? Y sub p in this case would be a e to the 5x. Cool? Third, what's up with an nth degree polynomial times cosine of ax? This probably... wait. Maybe I will go ahead and ask you to guess. If you said, oh, this is nth degree polynomial times cosine. Yep, nth degree polynomial times cosine ax. A generic one. Not quite. Okay. Apparently. Nth degree polynomial cosine ax or sine ax doesn't matter. In both cases, we should assume an nth degree polynomial times cosine ax plus another nth degree polynomial times sine of ax. What do I mean by another? Make sure that the constants are not necessarily the same. Like for instance, maybe I'll get to it when I have examples. Okay. So whether you have just an nth degree polynomial times cosine ax or just an nth degree polynomial times sine of ax, you must in the y sub p assume an nth degree polynomial cosine x plus nth degree polynomial times sine of ax. Okay. Second degree polynomial times cosine of 3x. Any guesses? Excuse me. Yeah, a second degree polynomial times cosine x plus second degree polynomial times sine of ax is what we assume. What do I mean by generic? Make sure that if you call these coefficients of the cosine of 3x as ax squared plus bx plus c, that of sine of 3x would be different from abc, that is def. Okay? So ax squared plus bx plus c times cosine of 3x plus dx squared. Cool. I'm sure you can guess this one. First degree polynomial times sine of 4x. So y sub p should be a first degree polynomial times cosine of 4x plus first degree polynomial times sine of 4x. As simple as that. Cool. All right. 4. What if we had e to the ax times cosine of bx or e to the ax times sine of bx? In that case, we just say e to the ax times a cosine of bx plus b sine of bx. E to the 4x sine 7x. We say y sub p is, can you guess? Yep, e to the 4x times a cosine of 7x plus b sine of 7x. So you kind of have to know this, and my hope is that it's logically following us to what we assume for y sub p logically follows what g based on the g of x that we have. Would you agree? Cool. Now let me actually solve a few problems. Is this a non-homogeneous equation? Yes, it is. Why? Because the right hand side is not equal to 0. Okay, so recall, when you have a non-homogeneous equation, you must find both the complementary solution and the particular solution and add them up to get the general solution. So the first thing we'll do is find the complementary solution y sub c. And how do we do this? Well, solve the associated homogeneous equation. That is, set this equal to 0, the differential equation to 0, and solve it. How do we solve this? Hey, it's a constant coefficients case. So 4.3, we really learned how to solve. We were pretty good at this kind of stuff, right? M squared plus m minus 6 is equal to 0, which implies m equals negative 3 and 2. So c1 e to the negative 3x plus c2 e to the 2x. These are unequal, real and unequal roots of the characteristic equation. So y sub c is c1 e to the negative 3x plus c2 e to the 2x. Cool. Now, to find the particular solution y sub p, based on the table in the previous slide, we need to look at g of x. It turns out g of x is 2x. Okay. What kind of a thing is 2x? Would you agree that is a first degree polynomial? So if g of x is a first degree polynomial, what should we assume? A generic first degree polynomial. That is, y sub p we should assume to be ax plus b. Cool. Notice a and b are constants that we do not know yet. How do we find them? Simple. Plug this into the differential equation, because when we claim that this is a particular solution, notice how I'm emphasizing solution. A solution must satisfy the equation, right? So this ax plus b must satisfy the equation. That means it must make the left hand side equal the right hand side when plugged in. So to do that, let's figure out what yp prime and yp double prime are and plug this into the differential equation. When we do, y double prime I plugged in 0, y prime I plugged in a, minus 6 times ax plus b for y equals 2x. And what happens? We get, if I collect all the like terms. What do I mean by that? Collect the terms with an x in it and collect the constants in this case. So when we do that, we have this, right? Okay, where do we go from here? What's our objective? Our objective is to figure out a and b, the unknown constants. The truth is, this must be an identity, which means this, what we got here, negative 6ax plus a minus 6 equals 2x, must be true for all values of x in the domain of whatever the solution is in the domain. For that to happen, the like coefficients must be equal. What does that mean? The coefficient of x on the left hand side must equal the coefficient of x on the right hand side. Similarly, the constant on the left hand side must equal the constant on the right hand side. If we go with that, then as simple as negative 6a is the coefficient of x, 2 is the coefficient of x on the right hand side, so negative 6a equals 2. But the constant on the left hand side is a minus 6b, whereas there is no constant, which means the constant should be taken to be 0. So we have two unknowns, a and b, and two equations, right? And we can solve for a and b. And turns out a is negative 1/3, b is negative 1/18. And so plug these a and b values into y sub p, and you get y sub p to be negative 1/3 x minus 1/18. And the total, or the general solution, is y equals y sub c plus y sub p. Take our previously computed complementary solution and add this to this particular solution. That's it. Cool. This is the process. understand every little piece of this thoroughly, and this is the same process I'll keep applying for a few more problems. Okay? Linear superposition of non-homogeneous equations. Ooh, what's up with that? Yikes. Let yp1, yp2, ypk be k particular solutions of the linear nth order homogeneous differential equation on an interval I corresponding to k distinct functions g1 through gk. Then yp equals yp1 plus yp2 plus plus ypk. All right. Clear as mud. Nah, it's not really that complicated. What it is saying is, when you are given a g of x, and let's say the g of x is composed of more than one function. Okay. What was it in the previous example? Man, I forgot. 2x. Yeah. So that g of x was a simple single function, 2x. But what if g of x is more than one function? Is that what we have? X square, 1, and 2 cosine 3x. So g of x is a combination of 3 different functions. Wait a minute. Do we really have 3 distinct functions? Or could I look at x squared plus 1 as just a second degree polynomial? The thing is, we could and we should look at x squared plus 1 as a second degree polynomial plus some cosine kind of a term. So what we are saying is this g of x is actually g1 of x plus g2 of x. Okay. Now, you probably are asking, what if I didn't recognize that I could say x squared plus 1 is just one single function, g1 of x? What would have happened if I said x squared is g1, this is g2, and that is g3? Hell won't break loose, but it's better to recognize the whole thing, the polynomial as a polynomial. Okay. Otherwise, you will unnecessarily have extra constants that you cannot solve for. I'll get to that in just a second. Okay. So in this case, because we have G1 and G2, corresponding to G1, we have a solution yp1. Corresponding to G2, we have a particular solution yp2. So the total particular solution is just a combination, linear combination of this. Just a simple addition. I wouldn't even call it as linear combination. Just a simple superposition of the two things. Superposition means is a fancy way of saying this plus that. Okay, even used to be in olden days, you would have people would write on what are those transparencies, and they would have one transparency and then they would put another transparency on top of this, right? So to create certain kinds of effects. That is called, hey, then we in the circumstance we would say, hey, the one transparency was superimposed by another transparency. It's just that you are adding two of them together. It's like same concept here as well. Okay. So yp is equal to yp1 plus yp2. Now I need to make an important statement here. This is the idea behind linear. Okay. When we have equations, differential equations that are linear, you can do this. In a way, when you think about this, what this is trying to say is if we were to have only g1 of x, we would have gotten a yp1, right? And if we had only g2 of x, we would have gotten some yp2 as a particular solution. But if we were to have both g1 of x and g2 of x as added together, then because this is a linear equation, you can simply add them. For nonlinear equations, things do not work like that. That is the key. So linear equations, thankfully, are a lot easier than nonlinear equations. Okay. That's the point I'm trying to make. Now, corresponding to x squared plus 1, which is a second degree polynomial, we will say ax squared plus bx plus c. That's the assumed one, right? Now, similarly, this is a constant, a first degree polynomial or 0th degree polynomial times cosine 3x. Corresponding to that, we will say d cosine 3x plus e sine 3x. Absolutely make sure that each of these constants is different. Okay. If by some chance you say ax squared plus bx plus c plus a cosine 3x plus b sine 3x, if you say that, it's actually wrong. Why? Because if you do that, you are claiming that whatever the coefficient of x squared is, that's got to be the same coefficient for even cosine 3x. There is no such stipulation. There is no such restriction. So don't force that kind of a restriction. Make absolutely sure that each of these constants is different. Okay? Cool. And, oh, man. What if, I think I'm about to say, what if we had looked at this as g1 of x, g2 of x, and g3 of x? Right? I told you hell won't break loose, but you need to do something. Corresponding to x squared, we would have ax squared plus bx plus c. And corresponding to 1, we would have a d. And corresponding to 2 cosine 3x, e cosine 3x plus f sine 3x, right? Earlier, we had only 5 constants. Now we have 6 constants. See? But the thing is, could we not combine these two constants, plus c plus d, into one single constant? And so this is actually ax squared plus bx plus some curly c plus e cosine 3x plus f sine 3x, in which case we have only 5 constants. That's the idea. So, yeah, look, I called it a c hat. What I called c plus d as some c hat, and e as some d hat and e hat. The hat is just that's a fancy way of saying some constant c, some constant d, and all that. They are equally arbitrary. Okay, so as long as you reduce the number of constants wherever it's allowed, wherever it's possible, then it doesn't matter if you fail to recognize the whole thing as being a first degree, second degree polynomial as opposed to 2 different polynomials. Okay? Cool. So right now I'm asking simply what to assume for y sub p. Suppose we have g of x equals 2x cosine 3x minus 3 sine 3x. Does it look like we have our g of x is comprised of g1 and g2? Is it or is it not? Is the question, right? It's a little tricky here. For a second, let's say, no man, that's got a x cosine 3x, but this is just a 3 sine 3x, a constant. So, okay, for a time being, think of them as g1 and g2. So, just looking at 2x cosine 3x, what would you assume as a particular solution for that? Notice, we have a first degree polynomial times cosine 3x. So, would you agree we need to assume a first degree polynomial cosine 3x plus a first degree polynomial sine 3x just for 2x cosine 3x? So, that's what we'll do. A first degree polynomial ax plus b times cosine 3x plus a first degree polynomial cx plus d times sine 3x just to take care of this g1. Now, plus negative 3 sine 3x. Don't worry about the negative 3. Hey, that's a negative, so should I subtract? And don't worry about it. Just make it a plus. If it turns out that your constants may end up being negative as a result of this being a negative, but you don't have to worry about it at this stage. Oh, no. I'm an idiot. Okay. It looks like I just treated the whole thing as 1. I didn't look at it as G1 or G2. No. Let's say this were to be G2. What should we have added? We have a 0th degree polynomial sine 3x. Corresponding to that, would you agree we should have added, where am I? I have a D. So E cosine 3x plus F sine 3x. Right? If we had treated this as a separate one, we should have added E cosine 3x plus F sine 3x. But wait a minute. Is that E cosine 3x pretty much the same as B cosine 3x? So we have already accounted for it. Or another way of arguing that is, if we combined, we would have had B plus E times cosine 3x. B plus E is an arbitrary constant, so we'll replace that with a B hat. Similarly, D plus F sine 3x is what we would have gotten. We can replace that with an arbitrary D hat. Okay, so it's okay in this case to just treat the whole thing as one g of x and not as g1 and g2. All right, what about this guy? What should we assume for this? Do we have a g1 and g2 in this case? 2x cosine 3x minus 3 sine 4x. If we were to say, nah, that's two different g1 and g2, okay, y sub p1 corresponding to 2x cosine 3x. First degree polynomial cosine 3x plus first degree polynomial sine 3x, right? Plus first degree polynomial, 0th degree polynomial cosine 4x. So that's what we would have. Plus, now, can we combine B cosine 3x and E cosine 4x? Nope. You cannot. I mean, you cannot in a regular sense, right? So, this is what you should assume as your y sub p, a linear superposition of yp1 and yp2. Cool? So, let me demonstrate this with a problem. Take a look at this. Y double prime, non-homogeneous, constant coefficients, non-homogeneous because right hand side is not 0, right? What was the procedure? First to find y sub c. How do you find y sub c? Set the differential equation equal to 0, and that's the associated homogeneous equation, and solve. How do we solve this? M square minus 8m plus 20 equals 0 is the characteristic equation. Find the roots of this, and trust me, that's 4 plus or minus 2i. And 4.3 says if that is the case, your complementary solution should be e to the, if you have alpha plus or minus I beta, e to the alpha x times c1 cosine beta x plus c2 sine beta x. We'll apply that concept here. And so we got e to the 4x times c1 cosine 2x plus c2 sine 2x. Cool. So this is the stuff we have become fairly familiar with. Now let's go to the particular solution, y sub p. Look at our g of x. Do we have a g1 and g2? Notice this is a second degree polynomial, whereas this is x e to the x, a first degree polynomial times e to the x. So yeah, so we should treat them as two separate g1 and g2, two separate things, g1 and g2. And corresponding to 100x squared, what would you assume? Second degree polynomial, so generic second degree polynomial, ax squared plus bx plus c. First degree polynomial times e to the x, so first degree polynomial times e to the x is what we assume for this. In other words, ax squared plus bx plus c to go with the 100x squared, and dx plus e to the x to go with the negative 26x e to the x. Notice I didn't care to make it into a subtraction. Are we good so far? So this is the key. Then, in order to figure out the constants themselves, we'll do precisely what we did in the other problem that we did, which is we'll plug this into the differential equation, the original differential, non-homogeneous differential equation. For that, we need to take a few derivatives, first and second derivatives, and let's go ahead and do that. I have done that for you and nicely arranged all the terms. Okay, and now when we plug this into the differential equation, we get this huge thing, right? Yep, there are a whole bunch of terms, but don't let that bother you. This is so then what I did is I collected all the like terms. So that means I looked at all of this and said, is there a term with just x squared times a constant? Yep, there will be a 20ax squared. Is there any other term on the left hand side with a constant times x squared? Nope, that's it. Now, is there any other term with just an x constant times x? No, not this one, because it is dx e to the x. So that's a different story. There would be a negative 16a. Right? We are looking for a constant times x. So negative 16a from here and a 20b from here. So plus x times negative 16a plus 20b. Okay, just constants. There's a 2a. There's a minus 8b from here. This is multiplied, no. And plus 20c. Right? That's what I have. Now, are there terms with an x e to the x in them? X e to the x. There is a dx e to the x. So x e to the x times d. And any other x, minus 8 dx e to the x. So minus 8d. And there is a plus 20d. So we have accounted for all of them. Like that, okay? And then e to the x itself, and set that equal to this. It's a bit laborious, I admit, but the concept I hope is very straightforward. What's the idea behind doing all of this? Now, the like coefficients can be set equal. Coefficient of x squared on the left hand side is 20a. And 20a is equal to 100. Coefficient of x squared on the left hand side equals coefficient of x squared on the right hand side. Coefficient of x on the left hand side is negative 16a plus 20b. Coefficient of x on the right hand side, there is no constant times x on the right hand side. Guess what? That means you just simply set it equal to 0. Okay? Similarly, there is no constant on the right hand side, so we'll set this constant equal to 0. Go on like that, and 13d. So, what are the unknowns? How many unknowns? 5. A, B, C, D, E. How many equations? 5. So those of you who are taking linear algebra, there's nothing fancy here. It's much more straightforward than the kind of equations that you will find in linear algebra. Okay. Clearly, from this you can figure out A is 5. The moment you get A, you can figure out B. The moment you know A and B, you can find C. Straightforward. D equals -2. So once you get D from this, you can figure out E. So even though it looks complicated, it's actually not. Okay. So A, B, C, D, E. And so y sub P is ax squared plus bx plus c. I'm just plugging in the values of A, B, C, plus dx plus e times e to the x. Right? So notice how our thinking of this as plus dx plus e didn't matter, even though this was a negative 26x e to the x. We didn't have to call this as minus. Okay, it automatically ended up that the coefficient of x e to the x turned out to be a negative quantity as a result. All right, cool. Of course, the last part is to say that y equals y sub c plus y sub p. You get the hang of this one? Cool. Next. What? This is an awfully simple problem. Compared to the previous two. Okay, let's see what the deal is here. Complementary solution y sub c. Set the equation to 0 and solve. M square minus m equals 0. M times m minus 1 equals 0, so m equals 0 and 1. Okay, so y sub c is c1 e to the 0x. E to the 0x is just 1. So c1 plus c2 e to the x. Right? Cool. We're done with the complementary solution. Particular solution, we need to look at the g of x, which is -3. So that's straightforward. This is a constant, so we'll assume a constant y sub p equals a. And this is ridiculously simple. Y sub p equals a. So what do? Plug this into the differential equation, so for which you differentiate once and twice, and plugging into the differential equation, we get 0, y minus 0 equals -3. 0 equals -3. Was that funny, man? I'm getting really sophisticated these days. I'm probably woke now. I'm looking at all the students and going, I need to use memes. So, So what went wrong here? So I just display it and move on. I don't want that guy to be, that kid is way too cute, man. He's a distraction. Go away. So 0 equals -3. So the whole idea was, there's some problem. There's some glitch. That's what the textbook called it. There's a glitch in the process. I like the word glitch. This glitch occurred for a particular reason. We really need to understand that. And the reason is, what did we assume for y sub p based on our g of x? A constant, right? Well, our complementary solution has a constant as one of its solutions. That's why we had a problem. If your complementary solution is a duplication of what you have assumed for particular, that leads to this particular glitch. Okay? So you should not assume y sub p equals a in this case. You should eliminate the duplication. How do you do that? And for that, to avoid the glitch, we must follow the following general rule. We must follow the following general rule. Whoa. If any YPI, meaning YP1, YP2, YP3, any of them, contains terms that duplicate the terms in Y sub C, then that Y sub Pi must be multiplied by x to the n, where n is the smallest positive integer that eliminates the duplication. Okay? Let me explain what in the world that means. We now have a duplication of what? Y sub p equals a. That constant is a duplication of the constant C1. So what this is saying is, to eliminate the duplication, multiply this by x. You could multiply by x square or x cube or x to the 4, but you must pick the power of x, which is the smallest one that satisfies this. Satisfies meaning that eliminates the duplication. Okay, so let's multiply this original one that we assumed for y sub p by an x and say y sub p equals ax. Don't go with it yet. Check again. Has this eliminated a duplication with the complementary solutions? Is ax a duplication of C1? Nope. Is ax a duplication of C2 e to the x? Nope. That's a completely different kind of function. So that means the moment we assume reassume the y sub p to be ax, everything would be fine and dandy. Okay, which does not duplicate any terms in the y sub c. Again, let's do the thing of figuring out the derivatives and plugging into the differential equation. And when we do, ta-da, we get a good, nice value for a. A equals 3. We don't end up with some stupid things like 0 equals -3. Everything is fine and dandy. So y sub p is not just 3, but 3x in this case. And we already had y sub c, so let's add the y sub c and y sub p to get the general solution. Cool? So this glitch thing is something you need to be very careful about. So in the next few problems, what I'm going to do is just talk about what to reassume so that there is no duplication. So those are the kinds of problems I'm going to look at. Okay, I'm not even bothering to give you what the differential equation itself. All I'm focusing on is I'll give you a complementary solution, which obviously came from a certain differential equation, and I'll give you a g of x. You tell me what to assume for y sub p. Of course, needless to say, making sure that there is no duplication at all. Cool? All right. If y sub c is c1 plus c2x, and g of x is 2x squared plus 3, what do we assume for y sub p? First, do not worry about the duplication part in the beginning. Just look at g of x and go back to what we learned. Is that a second degree polynomial? Yep, the whole thing is a second degree polynomial. So we will assume what? ax squared plus bx plus c. Would you agree? Cool. Now the question is, should we go with it? No. Check for duplication. Is ax squared a duplication of any terms in the complementary? Nope, there is no x squared term. Cool. Is bx a duplication? Yes it is. Bx is a duplication with c2x because a constant times x and a constant times x. They show up in both the complementary and the assumed particular. So we do have a duplication. And in fact, if we were to proceed, we notice that c is a duplication with c1. right? So what should we do? Right. And so we'll cross it out. I like to clearly cross the thing out. Clearly in the sense, don't scratch it. Just make sure that it's kind of visible, but at the same time nicely crossed out. So reassume. What should we do? We should multiply the original y sub p by an x. Okay? Whether we can go with it or not is a different story. So check again. Ax cubed, cool, no duplication. Bx squared, no duplication. Cx, Cx is a duplication with C2x, right? So we need to reassume. Reassume? By multiplying the previous one, the very latest one, by another x. Or in other words, we could have multiplied the original one by x squared, is the idea. Now any duplications? Ax to the 4, nope. Bx cubed, nope. Cx squared, nope. Cool, that's it. We can stop right here. So this is going to be our y sub p now. Cool. You get the hang of this? All right, I'll do quite a few more problems. Okay. All right. Y sub c equals c1 e to the 2x plus c2 e to the x, and g of x is 3x e to the x plus 2. What would we assume is the question. Notice we have g of x as a sum of two functions. Should we look at that as g1 of x plus g2 of x? Now pay attention to this example, okay? There's something very important that I'm about to point out. Do we have a g1 of x and a g2 of x? Answer is yes, we do, right? 3x e to the x is a certain kind of function, and 2 is as a constant. So corresponding to g1, what would we assume? First degree polynomial e to the x, right? So ax plus b e to the x. Corresponding to this constant, we'll assume a constant. But notice, it's important that you notice that it is made up of yp1 and yp2. Okay? Alright. Once we do this, again, let's go through this process. Are there any duplications? So we have ax e to the x. Is that a duplication? Ax e to the x? No, this is a constant e to the 2x. This is a constant e to the x. This is not a constant x e to the x. So no problem with ax e to the x. But we have a plus b e to the x. That's a duplication with c2 e to the x. Right? C, there is no constant. So there is no problem with C. The only problem is with this b e to the x. So how do we eliminate the duplication? We need to multiply by x. Now here is the trick. We need to multiply by x. We need to multiply what by x? Do we multiply only yp1 by x? Or do we multiply the whole thing by x? The thing is, this yp1 is separate, this g1 of x. So a term in the g1 of x or a term in the yp1 whose source is different from the source of the c, that's where the duplication is coming from. What I'm saying is, you need to multiply only the yp1 by x to eliminate the duplication. You do not multiply the c by this one because its source is different. Okay? So we multiply only the first one by x, and so we have ax squared plus bx e to the x, and plus c remains plus c. Cool? All right, so keep that in mind. What is the source? Yep, note no duplications. Note that since the duplication was the term in yp1, we multiply only yp1 by x and not yp2. That's it, eh? Okay, there are quite a few problems in this, just a laborious process, but I think I have taught you pretty much all the concepts here. So let's look at this problem. I like this one. I like this because it actually represents an interesting physical problem. The governing differential equation of a spring mass system, right? You have a spring, and to the bottom, the top end of the spring is attached to some fixed surface, to the roof, let's say, and the bottom end is attached to a mass. And the spring has some spring constant k, and the mass is m. K over m is this omega square. Okay, that k over m is the omega square here. And it is being subjected to an external force, f sub 0 cosine of gamma t. And the initial displacement is 0, initial speed is 0, initial velocity. I should call it speed. It's a scalar quantity. So initial speed is 0, right? So how do we solve this? Clearly, this is a non-homogeneous equation, so the process is the same. Complementary solution, and alpha is 0, beta is omega, and so y sub c turns out to be c1 cosine omega t plus c2 sine omega t. Cool? All right, then what? To find y sub p, since g of t is f sub 0 cosine gamma t, that means some constant times cosine of gamma t. You remember, 0 degree polynomial times cosine. So 0 degree polynomial cosine gamma t plus 0 degree polynomial sine gamma t. A cosine gamma t plus b sine gamma t. That's what we'll assume. Is that a duplication though? Is a cosine gamma t a duplication of c1 cosine omega t? If you say, nah, because this is a gamma and that's an omega, be careful. Why? Because did I ever say gamma is not equal to omega? What if gamma equals omega? Right? So, the right way of looking at it is as two separate cases. If gamma equals omega, there's a duplication and we do a certain other method. In fact, I think I have it worked out. Next problem where we will see gamma equals omega and see what the solution for that turns out to be. And for the other cases, gamma is not equal to omega, which means there is no duplication if omega is not equal to gamma. Let's pick that guy. Again, figure out yp prime and yp double prime and all of this stuff. And it's a tad messier. You get a times omega square minus gamma square equals f sub 0. So, okay, let me put your minds at ease. I'm not going to ask you this question in a quiz or a test. Okay? But I want you to understand something very nice. I'll discuss this fairly soon. Okay? To be able to talk about it, I'm doing this solution. In fact, those of you who would take, if you take ME 4060, I think Dr. Rao teaches it. So you would actually learn this in machine vibrations. Is it called machine vibrations or mechanical vibrations? One of those things. So in that course, you will learn in detail about systems like this. So anyway, so A turns out to be F sub 0 over omega square minus gamma square. Understand that F sub 0 is a known quantity, omega is a known quantity, and gamma is a known quantity. So we have solved for the unknown A in terms of all the known quantities. So y sub p turns out to be a cosine gamma t, right? Plus b sine gamma t, b is 0, so y sub p turns out to be this, and the total general solution turns out to be this. Okay. And now we need to, it's an initial value problem, so we need to plug in y of 0 equal to 0 into this. The whole idea is we are trying to find the constant C1 and C2 at this stage. And C1 turns out to be this, y prime of 0, and you get C2 to be 0, and so this whole solution reduces to this. Okay. Now, here is what I wanted to discuss with you. So what this shows is, let me see if I can draw this. If you have a spring and a mass attached to it, m and k, omega square is equal to m over k. Sorry, k over m. Omega square is k over m. And this is subjected to this external force F sub 0 cosine gamma t. This is a force that is being applied to this one. So we are trying to figure out what the position of this mass center would be. That's our y. We are solving for it. And our whole process, this whole solution tells us that y, the position of the mass center of the mass, is governed by this particular equation. Okay. So what's the big deal about it? Well, one big deal is we know exactly where this mass would be when subjected to this force at different times. Right? For example, think about, hey, if I go over in my car, if I go over a bump at such and such a speed, would the tires come back to touch the ground at a certain time, or how long will it take for the tires to come back and touch the ground again? So all those kinds of analysis require this kind of a problem solution. Okay. What is really fascinating about this is what happens if omega equals gamma. Okay. Notice omega equals gamma would cause the denominator to go to 0. Right? So we have F sub 0 over 0. So that means as gamma gets closer and closer to omega, omega is a natural frequency of this one. That means you have a given mass and a given spring constant. So omega is sort of fixed for that system. It's the external force which could be changing. We could change the external force. So suppose gamma were to get closer and closer to omega, the denominator is going to get closer and closer to 0. So that means this quantity is going to get larger and larger and larger. And what does this quantity represent? This F sub 0 over omega square minus gamma square? It actually represents the amplitude of a sine wave or cosine wave. Amplitude. So that means this will cause this system, this mass, the amplitude of the mass to keep increasing and increasing and increasing. Meaning this will start slowly going up and down and starts to move even higher and higher and lower and all that, and it'll just break eventually. Okay? And this is what is called the system going into resonance. Okay? When does resonance happen? When the frequency of the external force is equal to the natural frequency of the system, you get resonance. And in fact, that is the principle that radios use. In radio, what's happening? Some radio station transmits a signal at a certain frequency, 90.3 kilohertz, or is it megahertz? 90.3, right? And what do you do in your car? You tune the radio. What exactly does that mean? You are actually adjusting the frequency in your car when you tune it. And when the frequency that you are setting matches exactly with the frequency of the transmitted signal, you have resonance, meaning the amplitude is very large. In sound, the amplitude being large means the sound is very loud, which is what we say the sound is clear because it is loud. It's not just faded away and very inaudible. It's in fact very audible, very clear, very loud. So that's what happens in the case of a radio, resonance. Another example is the Tacoma's Narrows Bridge. The Tacoma's Narrows Bridge apparently was, when it was built, beautiful bridge. The problem was the wind in that particular area would blow with a certain frequency. And it so happened that this bridge has a continuous thing like that, has a whole bunch of natural frequencies, not just one single natural frequency like the spring mass system has. It has a whole bunch of natural frequencies. So it just so happened one day, one fateful day, the natural frequency of one of the natural frequencies of the bridge coincided with the frequency of the wind blowing. And as a result, the bridge started to sway slowly, and the swaying started to increase. That means the amplitude of the sway started to increase, and eventually it got to a point where the whole bridge just collapsed. Right? So that is the external frequency of the wind matching one of the natural frequency, and the system going into resonance is what happened there. Cool? So that's what I wanted to discuss, and that's why I picked this problem. In fact, I kind of lied. I apologize. I said, man, when gamma equals omega, this thing is infinity, or when gamma gets closer and closer to omega, this will go up and become a very large number. But wait a minute. Wouldn't this also go to 0? So wouldn't we have a 0 over 0 situation? You see what I'm saying? When gamma is getting closer and closer to omega, cosine gamma t minus cosine omega t is also getting closer and closer to 0. So we would have a 0 over 0 form. The truth is, we can reapproach this problem based on gamma being equal to omega. That means there's a duplication. Or we could actually be clever about this. We can use the concept of a limit, apply L'Hopital's rule, and figure out what is the limit of y as gamma approaches omega. And we can find a solution as to what happens when gamma approaches omega. That is one way. In fact, I recently worked the problem out like that, and I was amazed to see that the solution I got that way is exactly the same as the solution this other way. What is this? I went through the whole process in a very similar way, figured out the y sub c and g of t. Okay, notice I didn't, this gamma equals omega now. Okay, what happens if gamma equals omega is what we are looking at. And I went through this whole process. There is duplication. So we have to reassume I multiplied by t. Okay, because the independent variable is t, not x. And no duplications, and plugged all that stuff. And I'm not going to go through all of this. I'll have this in the notes so you can look at it if you are interested. And go through the equating the like coefficients and all that nonsense and applying the initial conditions. And finally, this is the idea. So the solution turns out to be f sub 0 over 2 omega times t sine omega t. Sine omega t is just a sine function, right? With a frequency of 2 pi over omega. So we have omega is the frequency of this sine function. And the amplitude is the curious one. Focus on that one. F sub 0 is a finite quantity. 2 omega is a finite quantity. Cool. So some finite quantity, some constant, times t. That whole thing represents the amplitude, f naught over 2 omega, f naught t over 2 omega. That's the amplitude. Can you imagine what physically that means? The amplitude is that. What it's saying is, as t increases, the amplitude increases. What? As t increases, the amplitude increases. Did I tell you that in the Tacoma-Narrows Bridge, first it started to sway slowly, and with time it just kept increasing and increasing and increasing. Finally got to a point where it collapsed. That's exactly what we're talking about. Amplitude increasing with time. If you plot this, this is how the graph looks like. It's all small, not a big deal. Whoa, but wait. If you stay like this, then it's going to get really large. Okay? So, folks, that's it. This is what I wanted to talk about. And we are done with entire chapter 4. Okay?